Hello and welcome everyone. This video is provided by Musa Rania, Miza Meher and me bin Mayasa Sara. Today we're gonna look to the buffer overflow. By the end of this video, you will have a clear idea of buffer overflow vulnerabilities, attacks, how to detect and prevent buffer overrun.
Have you ever heard about buffer overflow? Then join us in this video to understand and know how to detect and prevent buffer overflow attacks. In the end of this video, illustration will be given.
A buffer is a sequential section of memory allocated to contain anything from a character, string, to an array of integers. A buffer overflow or buffer overrun occurs when more data is put into a fixed length buffer than the buffer can handle. The extra information, which has to go somewhere, can overflow into adjacent memory space, corrupting or overwriting the data held in that space. This overflow usually results in a system crash, but it also creates the opportunity for an attacker to run arbitrary code or manipulate the coding error to prompt malicious actions. Many programming languages are prone to buffer overflow attacks. However, the extent of such attacks varies depending on the language used to write the vulnerable program. For instance, code written in JavaScript is generally not susceptible to buffer overflow. However, a buffer overflow in a program written in C and C++ or assembly could allow the attacker to fully compromise the target system.
How to detect buffer overflow? The short answer is just to pay special attention to where buffers are used, modified, and accessed. For example, when asking a user a yes or no question, it seems feasible to store the user string input in a small buffer only large enough for the string yes, as the following example shows. Looking at the code, it is clear that no bounce checking is performed. If the user enters maybe, then the program will likely crash rather than asking the user for a valid answer and reprompting with the question. The user's answer is simply written in the buffer regardless of its length, so the program's return address will be modified. This allows the user to force the program to exit the function at a different point in the code than originally intended, potentially causing the program to behave in dangerous and unintended ways. So, the first step to detect buffer overflows in the source code is understanding how it works, and the second step is knowing to look for external input and buffer manipulations. The third step is to know what functions are susceptible to this vulnerability and can act as red flags for its presence, like gets, strcpy, strcat, and printf. Anywhere one of these functions is used, there is likely a tool buffer overflow vulnerability.
How to prevent buffer overflow? The easiest way to prevent buffer overflow vulnerabilities is to simply use a language that does not allow for them. C allows these vulnerabilities through direct access to memory and a lack of strong object typing. Languages that do not share these aspects are typically immune. Java, Python, and .NET, among other languages and platforms, don't require special checks or changes to mitigate overflow vulnerabilities. If changing the language of development is not possible, we should use secure practices for handling buffers. In the case of string handling functions, you should avoid the strcpy and strcat. Functions copy a string into a buffer and pound the contents of one buffer into another, respectively. These two exhibit the unsafe behavior of not checking any bounds on the target buffer. One commonly suggested alternative to these are their associated strn versions. These versions only write to the maximum size of the target buffer.
Let's write simple code C that allocates some memory on the stack and copy a string into it from the command line. We are going to run something called GDB, which is Linux command line debugger. We can show the machine code for this, so we can say this is main and we can see this code for main. This line here, sub of 0x1f4 from ESP that allocating the 500 for the buffer. We can run this program from GDB, and if it crashes, we can look up at the register and find out where it happened. If we pass something that's over 500, then this buffer will go over this base pointer and this return value and break the code. So now we will print 41, which is the character A, 508 times. So we will exceed the buffer and override the entirety of our return address. Now the return address is overwritten with 41s. If there is some virus code at 41, 41, 41, that's a big problem. So we run this and you can see return address is 41, 41, 41. I can show you the register and you can see the constructor pointer is now pointing to 41, 41, 41. Now we can have a little bit fun. We've broken our code. What we can do? What we need to do is change this return value to some payload we're trying to give. So I have pre-prepared payload, which is an assembler program that executes a malicious code. Now we put in the buffer a lot of x90. That's a machine instruction for just move to the next one. Then we have our shell code. Then we have the return address right in the right place that points back right smack in the middle of this x90. So it's like having slope. Anywhere we load in here, it's going to be a problem. Then it will read off and run our shell code, so we should get shell. And we did it!
Well, this is the end of this video. I hope you enjoyed it. Thank you for watching.